Alright, welcome to some new slides. These are on probability. It'll be very fun. I have a lot of things I'm required to teach you about, but before we get there, I know this isn't like a statistics class, but this idea of correlation not being causation, I'm sure you've heard of before, hopefully, and it kind of has to do with probabilities at the same time. So here are some funny examples before we start. Apparently, eating cheese, per capita cheese consumption, correlates very well with the number of people who died by becoming tangled in their bed sheets over time. So those numbers match each other very well. So correlation does not imply causation, but maybe, I don't know, if you're superstitious, you should probably stop eating cheese. Okay. And then another one is global average temperature is apparently inversely proportional to the number of pirates that exist in the world. So the number of pirates has steadily declined, sadly, over time, and also the global average temperature has increased. So we should just create more pirates in the world, and that will definitely cause the temperature to go back down. Global warming is solved with more pirates, right? So obviously not, but this kind of stuff is the idea of probability, and we should talk a little bit about that now. So let's do it. So this slide is a pun, and you will laugh by the time I'm done with them. So let's talk about events. All right. So this is a technical term for probability. All right. We have a lot of terms I need to tell you about because it's a new topic we haven't really talked about yet. So okay, let's do it. So an experiment. All right. We say that an experiment is something you do. It's a procedure that results in one of a bunch of possible outcomes. So an experiment produces outcomes. All right. So you're going to flip a coin, for example. That's an experiment. Okay. Dun dun dun. You're going to flip a coin, and maybe it lands up heads, or it could land up tails. I don't know. It's head side up right now, but the outcomes of your experiment, right, is the coin lands on heads or the coin lands on tails. Okay. That's interesting. The set of all the possible outcomes is called the sample space. All right, the sample space of the experiment. All right, so the sample space of flipping one coin is this set. You could either get heads, right, or you could get tails. That's the idea there. And a subset of the sample space that you care about, maybe you really want heads, that's called an event. We would like the event heads to happen. And so that's just a subset. It's like, what do you really want? What pieces of the sample space would you really like? And that's a subset. That's an event. Okay. So that's all those terms all at once. We could write a graph of all the possibilities of what's going on, and that's called a probability distribution. So a probability distribution over a sample space is a function. If the sample space is called S, it's a function. We'll call that function P for probability from the sample space to the range of numbers between 0 and 1. All right, so this is the sample space 0 and 1, and it's inclusive. All right, so it's the number line inclusive. You got 0 at the edge here, 1 over here. They're both included, and anywhere in between. So your probability can be anywhere between 0 and 1 for every possible outcome. And yeah, that's the idea. So for example, when you roll a dice, you roll a die, a single die, right? The die could land on either 1, 2, 3, 4, 5, or 6. So the probability distribution, if it's a fair die, is here's the probability on the right. So this is the what's it called? The number on the die. And they're all equally probable, right? They're all equally probable. The probability of each of those rolls is exactly the same. So this is the probability axis. And they're all going to be 1/6, right? Because each of them has a 6th chance of showing up when you roll it. And that's actually very important. A probability distribution, every outcome, yes, the output should have a probability between 0 and 1, but the sum of every output, right? The sum of every outcome's probability better total to be 1, okay? Because that's 1 is the big final answer. That means always going to happen, right? So this is why it's 1/6 for each of these, right? It's 1/6 times 6 because they all add up now to be 1. That's important for probability land stuff. If you had an unfair die, right, it might be it might roll 2 or something more often than all the others, and that means the others have a smaller probability of getting rolled, right? Because it's still, all the outcomes need to, their probabilities need to sum up to 1. Okay, I hope that makes sense. And so that's a probability distribution, this kind of graph showing you the outputs, thinking about, really it's just a function, but we like to draw the function as a graph most of the time. And you can ask for the probability of an event if you have a sample, if you have an event that's a subset of your sample space. You can ask for the probability of that event occurring, right? That's just the probability of each of the pieces that might make up the event. So maybe I really care, right? I want to know the probability of the event that I care about is if the die lands on a 1 or a 6, like you win the game if it's a 1 or a 6 or something. So maybe that's the event that you care about, right? Because that's going to be a subset of the possible outputs, right? All the possible outcomes, and you can ask for the probability of that. And this is just saying that probability is the sum of each piece, sum of each individual outcome. So the probability of the event 1, you rolling a 1 or a 6 is the probability of you rolling a 1 plus the probability of you rolling a 6. Okay, I hope that makes a little bit of sense. So that's your example with die, right? You can only, hopefully you're going to roll a 1 or something. But you have 1 out of 6 options every time you roll something. Okay, so that's the idea there. You can also talk about whether the distribution is uniform or not, and that's hopefully every die is going to produce a uniform distribution. That's when it has every outcome having the same probability. That means you have a fair die, right? So that would be a uniform distribution if you have a fair die. Also coins, right? Coins have the same uniform distribution, right? Because if you have a fair coin, right, it's going to land equally on heads as it will on tails. So they both have 50% chance, right? So they both are 0.5, 0.5 for the probability axis. Okay, I hope that makes sense. So this is the probability on this side here, probability axis. So yeah, coins have a uniform distribution. That's one thing you can say. Uniform distribution, and just like everything else, right, the probability of every possible output for your probability distribution, for every possible outcome, they better sum up to be 1. So the probability of you getting heads plus the probability of you getting tails, that's 50 plus 50, or 0.5 plus 0.5, so that sums up to 1 total. All right, so that's important there. That's a lot of terms. Hopefully that makes a bit of sense, right? So uniform distributions are nice because every outcome has the same probability, and that means to get the probability of one thing happening, you can just divide by the total number of outcomes. So it's like 1 over 2 because there's 2 outcomes here. 1 over 6 because there's 6 outcomes when you roll that die. Okay, so I have to be very careful about the words I say now. I keep saying output instead of outcome, but have to be as precise as possible. So, all right, let's talk about combining events now, all right, because they might share some things, and that kind of ruins the day. So we say that 2 events are mutually exclusive if them as sets, if those 2 events represented as sets are disjoint. So like the probability of you rolling a 1, 2, or 3, that event, that is mutually exclusive from you rolling a 4, 5, or 6, that event. I hope that makes sense, all right? So that's really nice. Sometimes your events aren't mutually disjoint. Maybe they share some stuff, and so you have to do that. Those silly rules from before when we were counting stuff. Okay, so like in general, the union of events, the probability of their union, right? Probability of event 1 or event 2 happening, their union, is the probability of each of them separately. And if they're mutually exclusive, you're good, you're done. But if they have any overlap, remember that you've counted that twice. All right, so that's when you have to take that piece that you double counted and subtract. So it works for probabilities just like it worked for counting. All right, so this part though is nice and 0, set to 0 when they're disjoint. All right, so 0 when they're disjoint. Okay, you can also ask for the complement of an event. That's easy to figure out. What's the probability of the complement of an event? That's just when it doesn't happen. All right, so we say E bar just like we were doing Boolean algebra. So like, let's say that like here's your die outcomes. You have these possible ones, like 1, 2, or 3, 4, 5, or 6 over here. Maybe your event E was you rolling a 1 through 4. So like that was your event E. E bar, the complement of E, is every other thing. What's the probability of every other thing? That's the 5 or 6 happening. Do you see how that's going to be 1 minus, because they're supposed to add up to 1. The probability of this event, E bar, happening is the probability of the first one with a 1 subtracted out of it. Okay? That's the idea there. So that's E bar. It's just everything else. What's the probability of everything else? Well, it's supposed to add up to 1. So just like solve for E bar. That's the idea. Okay? So a fun complement example is called the birthday paradox. Surprisingly, and I'll show this to you in a second, it's crazy. Surprisingly, the probability that a group of n people total have at least 2 people sharing a birthday is very high, even for small n, surprisingly. When a group of 23 people, so like this class for sure people share a birthday, but even if you get a group of 23 random people together, you have a 50% chance that some pair of those people share a birthday, which seems really surprising and unintuitive, right? So the way that we solve for this and figure out the actual probability is by using the complement, because it's easier to frame this in terms of the complement. It's easier to first figure out what's the probability that no people in that group of n people shared a birthday. All right, so here's how you do it. It's a bunch of events happening together. So here is kind of the event that we're trying to, or the group of events that we're trying to specify when we're solving for the probability of the birthday paradox. What's the probability that a group of n people have at least 2 people sharing a birthday? So here's what we're going to find the complement of. Event 1 is if the person 1, like the person 1 just can have any birthday they want. They can choose from any of their pick, right? I'm trying to find the probability that nobody shares a birthday, all right? So event 1 is just like person 1 has a birthday. That's easy, right? That's easy to figure out. What's the probability of that? That's without considering leap years. It's like there's a 100% chance that person 1 has a birthday, right? 365 out of 365. And then event 2, we're trying to like figure out what's the probability that nobody shares a birthday. Well, that would mean for event 2 that person 2 better have a birthday on a different day than person 1, right? Now we used one of those days for person 1. It better be like for event 2, it's 364 now out of 365 options. That's the probability that person 2 did not share a birthday with the first person. You see that? And then you can keep on doing this. What's the probability, what's our next event, that the next person didn't share a birthday with this guy or this guy? What's the probability of that? Well, you've used up 2 days now, so now it's 363 out of 365. That's the probability that the third guy has a different birthday than the first 2. See that? And these are independent from one another, so to find the probability that this is all true at once, right, we can multiply them together. What's the probability of all these things happening at once? For n equals 23, for example, we're going to end up multiplying all this stuff all the way to like, what's the probability that the 23rd person didn't share a birthday with any of the previous 22 people? That would be 365 minus 23 plus 1 over 365. So that's going to be the probability we can solve for, and it happens to be 50%. It's really, really cool. All right, I'll show you that in Racket. But do you see how this is, the inverse of this, the complement of this will be 50%, because this is the probability right here that in a group of 23 people, nobody shares a birthday. Like the first person has a birthday, the second person didn't share with the first person, the third person didn't share with the first 2, all the way, like everybody has a different day. What's the probability that all those things happen at once? And then we'll take the complement of that to find the probability that at least 2 people shared. See that? It's the inverse that we really care about, but it's easier to frame it in terms of the complement and solve it that way. So I have a fun Racket example of that. So birthday paradox dot Racket. So here, I'll show you this one in a second. So I've made a function called birthday paradox that first gets the probability that everybody was born on a different day, and I'm going to multiply into this variable. Everybody born on a different day. All right. So I'm going to loop from all the variables for all the values that I need to care about. So like from 365 down to 365 minus n plus 1. See that? So that's the goal. And so I'm going in inverse order. So I'm making a range like this in Racket. So I'm going down to that number. And And I'm just multiplying into that was everybody born on a different day variable, keeping it itself times that value over 365. So that's this that I'm building up essentially. If n was 23, I'm building up this answer here in this variable. And so this is the probability that everybody was born on a different day. And so the probability that everybody, or that at least two people, right, that it wasn't true that everybody was born on a different day, that at least a pair of people shared a birthday, is the complement of that. So it's 1 minus the probability that everybody was born on a different day. And so for 23, bracket birthday paradox, for 23, the probability that everybody was born on a different day was 49-ish%, and it's 50%, or 51 essentially percent, if you round, that at least two people shared a birthday for a group of 23 people. So we've got about 50 students in this class. So the probability that at least two of you guys share a birthday is 97%. It's almost certain that there are two people in this class that share a birthday. Isn't that crazy? That's pretty cool, even though it's just a group of 50 people. It's very surprising. It doesn't make sense, but now you know how to solve for it, and hopefully it makes slightly more sense. So that's called the birthday paradox. It doesn't seem like it's right, but it is. All right, and we could test this if we were actually in class right now. So I'll share your birthdays on Discord or something. I promise. Two of you will share one. So there's that. All right, so let's talk about counting plus probability. They go together. That's why we had counting first. So here's an example for you to try. It will have to do with counting. All right, so let's pretend that we've got a drawer of n white socks and n black socks. So 2 n socks total, okay? And each white sock has a unique design, and each black sock has a unique design. So you can tell them apart, okay? So we are going to take 2 socks randomly out of the drawer, and every way of selecting 2 socks is equally likely. You didn't put them in any special order. And the order in which the socks are selected, though, does not matter. All right, so there's a lot of very specific probability words there. Let's see if you can parse them, and I'll tell you the answers for all these in just a second, but you try these. So first, how many ways are there to select the 2 socks? All right, given all these rules. All right, the order in which they are selected don't matter, but each of them are different. So there's like 2n separate socks in here. All right. Once you figure that out, how many ways of selecting the socks result in 2 socks of the same color being chosen? Like you want 2 white ones or 2 black ones, but they are all considered to be different ones, right? How many ways? And then what's the probability that if you take a pair of socks out, what's the probability that they were the same color, all right? And try to simplify. Hint, a lot of your answers will include something, choose something else. All right, so give that a try. All right, so how many ways are there to select the 2 socks? Well, the order doesn't matter that you're selecting them in. So how many socks are there total? 2n, right? N white ones and n black ones. And you're selecting 2 of them. The order doesn't matter. There's 2n separate socks, but you're taking 2 out of them out. So that's how many ways there are to pick out 2 socks, if the order in which you pick them out doesn't matter. Okay? So that's that one. All right, what about this one? How many ways of selecting the socks result in 2 socks of the same color being chosen? All right, so let's see. You can break that down into how many ways are there to select 2 white socks, and how many ways are there to select 2 black socks. Does that make sense? So that's like, all right, how many ways are there to select 2 white socks? So that's n choose 2, right? Because you got n white socks and you're choosing 2 of them. So there's n choose 2 ways to do that for the white socks, plus n choose 2 ways to do that for the black socks, right? You have the same number of black socks and you want to choose 2 of them. So there's n choose 2 ways to choose a black sock, or a pair of black socks. See that? That's the idea. And so simplifying that, that's 2 times n choose 2. And you can simplify that even further, right? Because n choose 2, that's going to be, how do you like, you got to pick the permutations, right? N times n minus 1. And then you divide by how many times you overcounted, which is 2 factorial. So that's just like over 2. And if we multiply that by 2, the 2's cancel. So that becomes just the top part. Right? So that's equal to n times n minus 1. That's how many ways there are to select socks, where 2 of the same color were chosen. All right, and this is how many ways there are to select 2 socks. All right, and so now A and B will help you here, right? what's the probability that when you take a random pair of socks out, they were both the same color? All right, try to simplify that expression as much as possible. And it's essentially the answer to B over the answer to A, right? It's like this is how many ways there are to do it right, where you have two socks of the same color being chosen. And this is the number of ways possible ever to take out two socks, so it's going to be this over this. See that? And so let's try to simplify it. Let's try to figure out this guy, 2n over 2, or 2n choose 2. That's going to be what? 2n choose 2. That's equal to, well, it's 2n times 2n minus 1 over 2 factorial, or over just 2, right? Over 2. And we can cancel out one of those 2's, right? So that's equal to n times 2n minus 1. And so it's going to be this guy over this guy. See that? That's going to be n times n minus 1 over n times 2n minus 1. And now the n's cancel. That's nice. So that's the final answer then would be n minus 1 over 2n minus 1. So that's going to be your probability. Interesting, huh? Interesting, interesting. It kind of looks like it's almost half, right? It's almost a half. It's almost 50%. But we have solved that without a doubt. That is going to be the answer. Isn't that cool? It's like to be able to know these kinds of things. Now we know, we have the tools. We know how to do it. So that's that one. I just have a bunch of examples for you like this today. So here's my next question for you. I believe that you can do it. It helps to write a program, actually. So here's my question to you. Which is more likely? Rolling a total of 9 when you're rolling 2 dice, or rolling a total of 9 when you're rolling 3 dice? All right, it may be counterintuitive, so think about it. Like, either you're rolling 2 dice, right, or you're rolling 3 dice. Is it easier to get a 9 when it's 2 dice? Like, is it more probable? Or when you're rolling 3 dice, right? Because now you have larger numbers when you're rolling 3 dice, right? Because you're getting the sum of all those values. So first, this is how you should break it down. What's the sample space for each experiment when you're rolling dice, right? 2 dice and 3 dice. What's the sample space? And what are the events you care about? It's when like the first dice adds up to plus the second dice adds up to something, or the first dice, second dice, and third dice add up to something, right? So think about that. It might help to write a program. So see if you can figure that out. All right, so first of all, the sample space. When you're rolling 2 dice, for example, you kind of know, you can, like the set of all the outcomes is what are the numbers on the dice. So like the first dice could be 1, the second dice could be 1, the first dice could be 1, the second dice could be 2, all the way to like they're both 6s, right? So that's your sample space for rolling 2 dice. And it's a Cartesian product, right? It's a Cartesian product of like 1 through 6 in the first piece and 1 through 6 in the second piece. It's equal to this, right? It's 1, 2, 3, 4, 5, 6. Those are the values for the first dice, for first die, I guess. And these are the values for the second die. Does that make sense? And so, same idea. What's the sample space for rolling 3 dice? That's likewise going to be that 3 times, right? It's going to be a triple of things. It's going to be 1, 2, 3, 4, 5, 6 per dice, per die. So that's like the Cartesian product of that 3 times, right? So it looks like, well, the first, they could all be 1s. You could have all rolled 1s, or maybe the first 2 dice rolled a 1 and the third die rolled a 2, all the way until they were all 6s. See that? So that's the sample space for each experiment. And then the events we care about for when we roll 2 dice, like we want to add them up, right? We want to notice that they rolled a 9, for example. So like here are my 2 dice. So like you rolled the 2 dice, and one, like if you're doing the example or the experiment where you're rolling the 2 dice, like one option is like a 6 and a 3, right? That adds up to 9. So like that's one of the outcomes we care about. Does that make sense? So what are my possible outcomes? I can never make a 9 if I roll a 1, right? Because the biggest could be 6. That would make 7. Same with 2, right? The biggest one for the next die would be 6. I could only make 8. So I have to start with a 3, right? It's a 3 and a 6 that make 9 for the first die and the second die for rolling 2. Or I could roll a 4 and a 5, right? Or I could roll a 5 and a 4. Or I can roll a 6 and a 3. Those are the 4 different ways to make 9 with 2 dice. See that? So the size of the event that I care about for 2 dice is 4. See that? There's 4 options there. And then for 3 dice, it's like, all right, you can have a 1. This one can't be a 1 because the biggest one here could be a 6. That would add up to 8 still. So it's got to be a 1, 2, right? 1, 2, then a 6. It's easier to program this, I promise. It could be then maybe a 1, 3, and a 5. Next, a 1, 4, and then the third die would have to be a 4, right? So that's the idea there. Let me rewrite that. It looks a little weird. But do you see how to represent what you care about here? That's important. And so let's go to programs to figure out what's the size of the event that I care about for rolling 3 dice. All right. So I've made a program for that. I've made it called Scratch here. So this first thing that I care about, I'll comment out these guys. All this stuff is for this first one. So I'm keeping track of all the ways, right? The count of all the ways to roll a 9 with 3 dice. So I'm going to set 3 iteration variables, triply nested for loop essentially. I goes from 1 to 6, same with j and k, and then every time I, j, and k add up to 9, I'll print that out, and then I'll increment my count and then print that out. The final count at the end there. Boop. So apparently these are all the different outcomes, all the different ways to add up to 9 for 3 dice. So we got 25 options apparently. Okay. So that's that one. It's much easier to write a program with just a nested loop. So there's 25 ways to do it for 3 dice. All right. And so the answer, right, is going to be the probability for rolling a 9 when you got 2 dice. It's going to be, right, the size of all the events, right, all the ways to the size of this event of rolling a 9, right, over all the different ways to roll 2 dice. What are all the possible outcomes? So the number of outcomes that we care about over the number of possible outcomes. So that's for 2 dice versus the same thing for 3 dice, like the number of ways to get a 9 for 3 dice over the number of ways to roll 3 dice. See that? And so that's what we're going to care about. So what's the size of each of those, like the sample spaces? So S2 is going to be, well, it's a 6 here, up to 6 options in the first piece and 6 options in the second index. So it's going to be 6 squared, right? 36. And then this one right here, for this one, it's going to be 6 times 6 times 6, right? Because you have 6 options for the first, second, and third piece. So that's 6 cubed there. So let's see. So this one's 4 over 36 versus 25 over, what's 6 cubed? I don't have that on the top of my head. 6 cubed is 216 apparently. All right, so which one is higher in probability? Rolling a 9 with 2 dice or 3 dice? So we got 4 over 36 versus, that's about 11%, versus 25 over 216, and that's about 11, so we got 11.1% and 11.6%. So just by a hair, it's slightly more probable when you're rolling 3 dice. Interesting. It's very, very interesting that it's so close. But that's the answer, and that's how you come up with it. There's like number of ways to get what you want over the number of total ways. All right, so that's probability in a nutshell. So I hope that makes sense. Here's another one that will help if you write a program. So next example I want you to try. So let's say that we're picking a number. We're picking an integer at random from the set of numbers from 1 to 50. What is the probability that when you pick that number, it was divisible by either 3 or 7? All right. So here is here's my hint to you, because like some numbers are divisible by both 3 and 7, so you've got, you have essentially this kind of union case going on. So like split it up into two events that are not mutually exclusive, because like you can solve for this part if you need to. So like split up into two different events. Call it like E3 for the numbers that are divisible by 3 and E7 for the numbers that are divisible by 7. Those can be your two events, and you want to find the probability of their union. All right. So again, it's probably helpful to write a program to see which numbers are divisible by both one or the other. Okay, and then to calculate that union, you'll use this formula. All right, so that helps us not double count things. So give that a try. All right, so the very first thing we need to do is like, what are all the numbers that are divisible by 3, right? E3. That's 3, right, between 1 and 50. That's the set we're choosing from. So 3, 6, 9, 12, ... all the way to, I think it's 48, right? That's the largest number that's divisible by 3 in this set. And then E7, what are all the numbers that are divisible by 7? That's going to be all the multiples of 7, right? 7, 14, 21, 28, 35, 42, 49, and 49 is the last one there. So what in the world is the size of E3? What in the world is the size of E7? E7 is at least easy to figure out how big it is. That's exactly 7 numbers, right? Because 7 times 7 is 49. And then what's the size of E3? How many numbers are divisible by 3? In the numbers from 1 to 50. We'll figure that out. And then we also have to figure out their intersection, right? Because what we would like to do is calculate this probability. The probability of E3 unioned with E7. And that's going to be equal to the probability of just E3 happening plus the probability of just E7 happening minus the probability of their intersection, because there will be an intersection. There are numbers that are both divisible by 3 and 7. And so we'll have double counted them, and we have to get rid of that double counting by doing that subtraction there. All right, so yeah, I've also written a program, and I encourage you to do the same, that does all this, counts all the numbers divisible by 3, 7, and both. All right, so here's some functions. This one is a function that, like, I'm keeping counts, right? All the numbers divisible by 3, 7, and both. And here's how I check if a number is divisible by one or another, right? I do their modulus, right, and check that it goes in cleanly, that the result was 0, there's nothing left over. And so I do some silly stuff to like increment variables more easily, but essentially I'm just going to loop. I'm going to loop from 1 to 50, and if it's divisible by both numbers, I'll increment all of those variables, because it was divisible by 3, 7, and both at the same time, so I got to increment all these guys. If it's just divisible by 3, I'll increment divisible by 3. And if it's just divisible by 7, I'll increment the divisible by 7 variable. All right, so I'm counting them all up. And here, oh, did I not save it? There we go. And so apparently, the number that are divisible by 3 is 16. So there's 16 numbers divisible by 3 here. And there are two numbers that are divisible by both. And so it's going to be, if it's divisible by both 3 and 7, so like 21. That's a number that's divisible by both 3 and 7, right? So it'll be in here, and then also in here. And then also that, I think that times 2, 42, right? Is it 42? Yeah, I think it should be 42, yeah. And then also 42, those both add up. That's also a multiple of both 3 and 7 at the same time. So those will be in both, and so we got we're double counting twice there. So the size of E3 intersect E7. Sorry, that intersect E7 is equal to 2, and of course all the numbers is 50. There's 50 numbers total, right? So now we can calculate our probability. So what's the probability that a number is divisible by just 3? Well, it's how many ways are there to do it over how many ways total. So if we pick a number at random, there's a 16 out of 50 chance that that number was divisible by just 3. And then for 7, same game. It's like, all right, there's 7 ways to be divisible by 7 out of those numbers, 7 options out of 50 options, right? There's that one, so that plus that, then minus the probability of both of these happening at once, minus 2, right? 2 over 50. And so what's this output? 16 plus 7 minus 2, so 16 plus 5. That's 21. 21 over 50. So it's a little under 50%. That'll be our final answer there. Okay? Does that make sense? That's the probability that if you draw an integer randomly from that bag of 50 numbers, 1 through 50, that's the probability that's divisible by either 3 or 7, or both. 21 over 50, it's a 42% chance exactly. That's pretty cute. All right, that's a good number. All right, I hope it's a little bit of a review, right? You've learned about probability before this class, but we're hitting it with sets now. That's the new thing, okay? Let's next talk about a slightly more complicated topic called conditional probability. This is when we want to condition on. If we know something happened, does that change the probability of some other thing happening? All right? It's like, given that it's cloudy outside, what's the chance of it raining? It's probably the chance goes up if it's cloudy outside. Right? That's conditional probability. So here's this spelled out. If you know that some event F happened, sometimes that gives you a more accurate idea of whether some event E also happened. Okay, that's the idea. So, for example, here's all the different possible events, or all the different possible outcomes of an experiment. There's a bunch of them. All right, all of our possible outcomes, and then here is event F. All right, we know that event F happened. So if this is event F, these are all the ways that F could have happened. Just like that. Here are, and then we also care about, did E also happen? So where's event E? Sometimes, a lot of the time, they share stuff. So like here's E. Sometimes you can gain a more accurate picture. If you know that F happened, you can get a better chance of knowing, hey, did E also happen? Because look where you can zoom in, right? Just by default, originally, let me make that a bit smaller. What's the probability of E happening by itself? It's just like the size of E over the size of everything, right? What's the probability of F happening by itself? It's the size of F over the size of everything. But if you know that F happened, you know that you're here, right? You know that you're one of these dots within here. See that? So you've zoomed in a little bit. That's pretty nice. You can change. You have more information, right? Things might change because of that. And so you know if F happened, here's all the ways that E could have happened and F at the same time, right? It's these that they share right here. So now what's the probability that E happened if you know that F happened? It's this guy over all of F. See that? And that might give you a better, more accurate answer. I hope that makes sense. All right, so that's called the conditional probability. We say of E given that F happened. So E given F for short. All right, so what's the probability of E given that F has occurred? E given F. And you write it like this. So that's this little pipe character that stands for given. What's the probability of E given F? All right, that's the probability of E happening when you know that F happened. So it's exactly what I was saying here. It's the probability of their intersection. You count their intersection, all the ways to do both at the same time, over, because you know F occurred, you know that you're in here, so you can just count all of F. So it's the probability of E intersect F over the probability of just F. So that gives you a more accurate picture a lot of the time, okay? So that's conditional probability. And we say that, now that we have that term under our belt, we say that two events are independent of one another if conditioning on them, one versus the other, doesn't really change anything. All right, so two events are independent if conditioning on one event does not change the probability of the other event. That means they weren't influencing each other. Okay, so here, for example, is an example right here. This is an example of two independent events, E and F. We can condition on each of them. All right, so just to solve though for the conditional probability, let's solve for the probability of E given F. Right, so what is that? That's equal to, right, what are all the ways to make both, right, their intersection? If we know that F has occurred, what's the probability that E occurred, given that F has occurred? It's these guys, right, over all of F. So it's going to be 2, right? There's your intersection of E and F. That's this part. 2 over all of F, the probability of just F. There's 6 ways for F to have occurred, right? So over 6. 2 over 6, so that's 1/3 chance. So probability of E occurring, if you know that F occurred, E given F is 1/3. And this happens to be an example of 2 independent events. So let me show that to you. So they're independent if conditioning on each of them doesn't really change anything. So that's like the probability of E given F just ends up being the same as E, right? So these are 4 different ways to say that 2 events were independent from one another. So these are all equivalent. So E and F are independent, that's one way to say it. Or conditioning on E, the probability of E given F, which we know is this, ends up being the same as just asking about E. F didn't really give us any new information. The probability of E given F is just the same as the probability of E. And then the same is true vice versa. The probability of F given E, which we know how to calculate, it's like that. That just ends up being the same as just taking the probability of F. Knowing that E happened changed nothing. They did not influence each other, they were independent, all right? And then if we solve, there's a way to solve for these equations. You see how like, if they're independent, how do I want to do this? If they're independent, this ends up being, right? This ends up being true here. P, if they're independent, like this is one way to say it. And, all right, the way you get here is you just multiply each side by the probability of F. You see how if you multiply that, bring it onto this side, that gives you this equation, and it'll also give it to you for this one way or another, okay? I hope that makes sense. So like that's how you end up with the last equation. You just like take this idea and you just bring the F to this side, okay? So that's how you end up with the last one. And so all of these are equivalent statements, okay? That's going to be the idea. All right, so let's show that these 2 events really were independent. All right, so let's say, what's the probability of just E happening? That is 3, right? There's 3 options for E happening. And how many options total for everybody in the whole universe of options? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 3 over 9, which is 1/3. And what do you know? Conditioning on F did nothing. So that means they're independent. That's one way to say it. And then we can do the same for F, right? Probability of F. We'll try that one. Probability of F is, you got 6, right? 6 options out of 9 total. That's 2/3. All right. And what's the probability of their intersection? So we can solve for this using this formula this time, because we counted this way. That was the easy way. But this formula also works. So let's do the probability of E intersect F. Boop, intersect F. That is equal to, well, 2, right? 2 over all the options again, 2 out of 9. See that? So that now we can use this formula to calculate in the other standard way of probability. What's probability of E given F? We know it's going to be 1/3, but let's just watch the numbers work out. All right. So that's going to be what? Probability of E intersect F. So it's 2/9. 2/9 over probability of just F, which was 2/3. Over 2/3. Do your cross multiplication. You've got the 2's cancel, I think. No, they don't. It's 2 over 9 times, so it's 2 over, gosh, I can never do this right. It's 2 times 3 is 6, right? 6 over 9 times 2, so 18. It's been too long. And so that is 6, 12, 18. So that's 1/3. So that's another way to calculate it. But you can just count dots if you have the dots. But these are independent because we determined that, well, the probability of E given F is still 1/3. That's the same as the probability of E. So conditioning on F did nothing. So that means we notice that they're independent, just like that. All right. So that's important. 2 events being independent from one another, they have no effect on each other. That's something you care about a lot, especially when you're making some trials for drugs or stuff like that. Okay. So now that we know about conditional probability, knowing whether something happened, given that we know something else already happened, I can show you a very fun example. It's a classic one that everybody teaches when they learn probability. in this kind of class. It's called the Monty Hall problem. So apparently there used to be a game show. I think it was in the UK, but I haven't looked this up too closely. But this used to be a thing. All right, so this was your game show. There are 3 doors. 3 doors labeled 1, 2, and 3. Here they are, 1, 2, and 3. And there is a car that you could win, right? There's a car behind each one of the doors. So like here's the door with the car. My old drawing of a car. So there's one car behind the door, one of the doors, and then there are goats behind each of the other doors. Okay, so there's 2 goats behind each of the other doors, and you of course have no clue which one has the car and which have the goats. So the way the game works is you say, I would like to open door 2, all right? And then the catch is, or the trick of the game, like it could be over at this point and you lose, but no, they made the game cooler. You say, I'm thinking about door 2, and then it's Monty Hall because apparently the host his name was Monty. So if you say, I'm thinking about door 2, Monty then will open up one of the doors with a goat, guaranteed. So Monty will open up, if this is what really is behind the doors, he'll open up door 3 now, all right? And you get to see that there's a goat behind door 3. And he'll ask you, would you like to keep your guess of door 2, or would you like to switch to door 1? All right? That's the game. And so the question is, probabilistically, is it better to swap your guess, like go to door 1, because like you had no clue which one had the car, maybe this one really did have the car. Or is it better to keep your original guess? So that's the game. Like you get a door open, you definitely are going to see one goat, and then your question is like, do you keep the door you picked, or do you switch to the other one? Is it better to swap or to stay? All right. And so this is a very, very weird proof that has to do with, I guess, just intersections, more or less. All right. So actually, it's better to switch. It's always better to switch. And let me try to give you a hand-wavy proof as to why. All right. So what is the probability, right, if you didn't switch? If you didn't switch, let's see here. The probability that you stayed, you kept your original choice, and you got a car, right? That's just the probability, did you guess right the first time, right? What's the chance that you picked the car the first time? That's a 1/3 chance, yeah? So that's the probability of you staying and getting the car. And so then what's the probability of you switching and getting the car? This is the secret. Well, if you switch and get the car, what's the probability that the car is behind the door that you get? So here's the weird hand-wavy proof. So like here are your doors, right? And you say, this was your original pick. Like you're not sure what's behind this door, you're not sure what's behind this door. You know, right, that there's going to be a goat, right? There's a door that's going to be open to you and you're going to see the goat. And so if you switch, you're guaranteed to go to this one, right? You're guaranteed to go to this one. What was the probability that the car was behind either this door or this door, right? It was 2/3. Do you see? The probability that the car was behind this door or this door, it's just like 2 out of 3, right? And you are going to get to see the goat in one of them, so your hand is forced on the other door, and so that door is going to have the whole 2/3 chance of holding a car. All right? That I know is a weird hand-wavy proof, but that is actually the secret to it all. It's like the probability that you didn't make the right choice at the first chance was a 2/3 chance, right? That the car was behind one of the other doors. You get one of those other doors open for you, so the whole 2/3 chance of there being a car goes to that other door, right? The door that you didn't pick, that didn't have a goat behind it. So that's why it's 2/3 there, all right? So it's better by a lot to switch always. It's really unintuitive. A lot of mathematicians argued with each other about this for a while. It's a very famous problem, but we can just show ourselves, we can prove it to ourselves by writing a simulation in Racket. We'll count the number of, we'll just pick random numbers and count how many times we win if we stayed, kept the same door, and how many times we won if we switched doors. Okay, so let me show that to you just really quick. So here's the Monty Hall program. You can read it closely, but I'm going to run 1,000,000 simulations, 1,000,000 times of playing the game, all right? And so here, every time we simulate, we're going to pick which door contains the car, and we're going to pick which door we pick. It's a number between 1 and 3, right? And then, all right, if we'll count how many times we win by staying and how many times we win by switching the door, all right? So we win by staying if the door that we picked ended up being the door that had the car, right? That's how many times we win if we stayed. And then, all right, if that's the original door that we pick, right, we have to like figure out like which is the door that we reveal. It has to be the one that doesn't have the car still, and it has to be the one that we didn't pick at the same time. So like figure out which door that we're going to be revealed to us. So like we're going to get that one. And then that leaves one last door that we could switch to. It wasn't the door that we picked, and it was not the door that was revealed to us. And then we check, was the car behind that door, the door that we could possibly change to? And we'll add one if we can get there, right? So here I am running simulations a million times, like starting off at 0, of course, all right? So at the end, once I've run all my simulations, I'm going to print the results. How many times did we win by staying? Out of the 1,000,000 times that we play the game, how many times could we have won if we changed the door every time? We always switched. And then also the probabilities. Just, it's over 1,000,000, right? How many times did we win over 1,000,000? Monty Hall. And so, there it went. Do you see, without a shadow of a doubt now, if you stayed, you won this many times, it's a third chance. If you changed, you always switched doors, you win with a 2/3 chance. And hopefully you can kind of see why, all right? So it's really unintuitive, and this is exactly why, like one day you're going to make a program that uses random numbers, you need to learn how to prove that it's going to be right most of the time, okay? Or that it's going to get to the right thing. So this is why we're learning this kind of stuff, so that it becomes slightly less unintuitive, all right? So yeah, the last thing that I want to talk about today is a question for you. I want you to try this as best as you can, and then I'll show you the answer. It has to do with conditional probabilities this time. All right, so, all right, we got some letters. The letters A through G are put in some random order, all right? So we're getting a permutation of those letters. Every permutation is equally likely. Here are some events, all right? Event A is if letter B is in exactly the middle of that permutation, right? With 3 numbers before it and 3 numbers after it. So this is like event A. Like this is one possible way that, one possible outcome in event A. It's like you got A, D, C, B was in the middle for sure, and then G, F, E. Like that was one way to do it, where B was in the middle. You got plenty more. All right, so that's event A. Think about that. Event B is if the letter C is always to the right of B. It doesn't have to be exactly to the right, but it's somewhere to the right of B. Right? So B appears before C. That's what we're trying to say. So for example, this one, this would be an outcome in that event. So B is coming before C. It doesn't have to be immediately before C, but it has to be there. So like anything where B comes before C, those are those outcomes. If C came first and then B came later, don't consider that one. Don't count that one. All right, so that's event B. And then finally, event C is the letters D, E, and F occurred together as one big chunk. All right, so like this is an example outcome in event C, where D, E, and F appear together, and then everything else can appear in some other place. It's fine. All right, so like that's what you do. It's one big chunk there. And so what I'd like you to do is calculate the probability of each of those individual events, probability of A, B, and C, and then calculate the probability of A given C, A given B, and that's going to require you to calculate some intersections, right? Probability of A intersect C, probability of A intersect B using this formula, so keep that one in mind. And then, using what you notice, right, because you have these rules, tell me, are A and B, those events, independent from one another? And are A and C, those events, independent from one another? So give that a try. All right. So let's do all this together after you've tried it. So the probability of A, where the letter B fell in the middle somewhere. All right. That's going to be the goal there. So what are all the different ways, right? What are all the different ways for B to be exactly in the middle? Well, it's when you fixed that. You fixed exactly this happening right there only, and so your only choices, your only other options are where to put the other 6 letters, right? And you can rearrange them in any way. So what are all the different possibilities of arranging 6 other letters where B is stuck in the middle? It's 6 factorial, right? Because it's only those 6 things that you're allowed to move, and then it's over the number of ways total to like permute the letters, and that's because there's 7 letters. It's 7 factorial, right? Because they're each equally likely, so that's A. So that's probability of event A. That's probably what I should say here. That's probability of A equals that. Probability of, or this is all still part A. Probability of B is what? Event B, the letter C appears to the right of B and vice versa. Let's see, is not true. If you think about it long enough, the number of ways that you could arrange the letters where B comes before C, there are exactly as many of those as there are ways to arrange the letters where C comes after B. Or sorry, C comes before B and C comes after B. I hope you see that. So it's really just a 50-50, right? There's a 50% chance that you're going to get B coming before C rather than after it. There's equally number of ways in both outcomes, right? Both options. So it's for sure 0.5 there. Hope you see that. And then probability of event C, the letters D, E, and F occur in that order, and everything else can appear in any other place. The secret there is just to consider D, E, F, that string, to be one big chunk, one big character by itself. Is one big character, right? So that's the secret there. And so it's just one character, and then that means you have 1, 2, 3, 4 other real characters that you can permute with it. This is the 5th character, right? That has to all stay together. And so it's 5 factorial ways, right? Because it's just like the 5th giant character. So 5 factorial ways to have that work out over 7 factorial ways to permute all the letters. All right, so now we're ready for parts B and C. So what's the probability of A given C? Probability of A given C, that's equal to, right, following our formula, probability of A intersects C over the probability of C. So we know probability of C. Well, let's do the rest. What's the probability of A intersect C? Now, I'll admit that this is tough to figure out, like, when is it true that event A and event C have happened at the same time? So, like, letter B is in the middle and D, E, and F are together. Let's think about this. So, all right, if B is stuck in the middle, we know it looks like this, and then D, E, and F have to go together, do you see how either the D, E, and F was over here, and the only thing you have control of are these blanks right here, or still B was in the middle, right, and D, E, F went over here as a chunk, right, and then you had only control over these things. So now you have, like, the rest of the letters, there's 3 letters left, 3 factorial ways on this side, 3 factorial ways on this side to make it look like that and have both at the same time. So that's the secret, right? 3 factorial ways to make it look like this, and 3 factorial ways to make it look like this. So 3 factorial plus itself. So there's 2 of those over the number of ways total, so over 7 factorial. That's the intersection. And then probability of C is 5 factorial over 7 factorial, which is, let's just write that as P of C. And I'll let you solve for whatever that is, okay? But that's going to be the answer there. And, or maybe we'll solve it later because we have to figure out independence. But I'll go to Python with that. That's too much effort. Too much effort right now. All right, let's do the next one. Probability of A given B. So following the formula again, that's going to be the probability of A intersect B. So both of those things happening at once over the probability of just B happening, which we already know, all right? So let's figure out this one now. So this is, okay, we know that B is in the middle still, and then C's got to appear to the right of B for sure, okay? So let's think about this. Well, this is kind of what our blanks look like. We know, we've got 7 blanks, right? Our hand is forced for B. It's forced right there. And then C, right? These could be anything but C, right? And then C could go in any of these. Like the blanks are here, but C has to be either in this one, or this one. Do you see that? And so really, your hand is kind of forced. Like you can pick, like, maybe C should go here. And at that point, right, you have possibilities for the other 5 characters. Does that make sense? So you've got 5 factorial ways to make it look like this, where C's in that bit. And then you could just move around C. It's like maybe C was here and the rest were blanks. There's another 5 factorial ways. Or maybe C was here and then these were the other 5 blanks. So you have 5 factorial options for each of those ways, and there's 3 ways to put the C. See that? 3 ways to put the C to the right of B. And you have 5 options left for everybody else. So you have 5 factorial ways, once you've picked where C should go to, 5 factorial ways to do that, and you have 3 places you could put the C. So that's your total number of options. And so all that over 7 factorial. There's your probability there. And then over the probability of B, which I'll just write PB to make it easier for ourselves. And then our last piece of the puzzle is like, are A and B independent or are A and C independent? And to figure that out, right, we just check, like, was the conditional probability not giving us anything? Was it the same as just the probability of that first thing? All right, so let's figure this out. So D, well, probability of A given the probability of C, what is that? Well, let's do the calculation, I guess. Oh, and I just noticed I forgot to write something out. So to get, going back to A given B for a second, to get this idea, like this picture is almost saying everything. It's just like, to place the B, there's one way to do that. And then the C could go in any of these 3 spots over here, times 3. And then you have 5 digits or characters left to choose from, and so that makes 5 factorial. And then that's all over 7 factorial. That's another way to think about it, okay? So maybe that's easier. So that was that. I forgot to write that, sorry. So, all right, now back to A given C. I think the easiest way to do this would be to just calculate what in the world is this. Go to Python. Help Python. So if I import math, I do believe I can get this good enough. So I can get like PA, I think, in code. I'm going to have to compare that eventually anyway. So the probability of A is 6 factorial over 7 factorial. That's math.factorial 6 over math.factorial 7. That's the probability of A right there. And the probability of C is something I'll have to divide by. So P underscore C, that was 5 factorial over 7 factorial. So I can actually use most of this. PC is 5 factorial over 7 factorial. And then their intersection was this bad boy, 3 factorial plus 3 factorial over 7 factorial. PA and C is factorial of 3. I have 2 of those, right? 2 of those, then over 7 factorial, right? Over 7 factorial, and that's just the intersection bit. Over math.factorial of 7, and all right, then to get the conditional probability of A given C is probability of their intersection over the probability of C. So PA and C over the probability of C, that's apparently, ooh, perfectly, a 10th chance, crazy, cool, 10%. So, and then let's compare that to the probability of A, right? How does that compare to the probability of A? If it's equal, they're independent, right? So what's the probability of just A? That was about 14%, so they're different, all right? So it's not the same. So because they're not the same, that means they're not independent, all right? Only if they were the same were they independent. So I'll do that. And then, so we can conclude that events A and C are not independent. Okay, this is a harder problem, but it's a very good one to practice with. And then for the last one, our A and B, or sorry, yeah. Why did I do AC first? I guess I did that last time first, sorry. A and B, let's check those. That's just like, hey, how does this compare? A given B, is that equal to the probability of just A? Well, let's find out. How does that compare to the probability of just A? Let's figure this out. So A given B is, all right, what's the probability of A intersect B? Let me write that out. P, A, and B is 3 times 5 factorial over 7 factorial. That's just the intersect part. 3 times 5 factorial over 7 factorial. So 5 factorial, 3 times that, all over math.factorial 7, and that'll work given the order of operations. And then, so it's that, A and B, and the, or sorry, the answer is that, and B over the probability of just B, which was, that one was easy, it's 0.5. 0.5. So that's 14-ish%. Is that equal to the probability of A? It is. Ooh, so A and B those events are independent. So knowing that B occurred, conditioning on that, does not change the output or the outcome for A at all. Those are independent of each other. They are not influencing each other in any way. So that's fun technical concepts that we have to know to do cool things later. But it's still kind of useful to be able to break down these problems. We know how to do it now. So definitely give these a practice. It's a harder topic. There's a lot of things that I have to say exactly precisely. And so it's fun for me too. But we'll get through it together. And yeah, that's where I want to stop right now, and I will see you in the next one.